So we're going to get into ionic bonding here. And first, just a quick review of ions. Ions are atoms that have a charge because they have gained or lost electrons. Remember that atoms do not change their number of protons. It's not possible in a chemical reaction. It's not possible in chemistry. We cannot cause atoms to change their number of protons, and so instead their charge comes from a gain or loss of electrons. Positive charge comes from, and this is where I would normally ask you, so I want you to think about it here for just a moment. You certainly can say it out loud, but positive charge comes from losing electrons. And again, that's because then what happens is if you lose your electrons, the number of protons is going to be greater than the number of electrons. On the other hand, negative charge comes then from, and this one here should be more obvious, gaining electrons. And that's going to be because when it gains electrons, then the electrons will be greater than the protons. I suppose I should have stated to begin with, as well as a reminder, that neutral atoms that have not become ionized yet, ionize the process of becoming a ion, protons are equal to electrons, which are equal to the atomic number. And so then if you lose electrons, then the number of electrons goes down, and you end up with fewer electrons than protons. If you gain electrons, then the number of electrons goes up, and you end up with more electrons than protons. And again, a reminder, each atom will only gain or lose electrons on its valence shell to either empty it out, and if they empty it out, then the prior level was filled up, and so then its outermost energy level is full, or to fill it up, in which case the outermost energy level becomes full. And as a reminder, and again, this is a place where I would normally ask you to tell me, but this is the octet rule, because a full outer shell usually means 8 valence electrons. Something new here on this slide, there is a thing called a polyatomic ion, and a polyatomic ion is a ion formed by a group of atoms working together as if they are a single ion. And so they are usually negatively charged. There's one exception to that on your list that you will have, and you do not need to memorize these. This is a list that should have been handed out here. You will be allowed to use a list like this on the test. The list that you have, feel free to mark up. You'll either be given a new list, or the list will be frozen up on the screen when you take the test. And if you ever need to refer to it, it is on your textbook on page 158. I was lazy for quite a few years and did not take the time to type up my own list, and so we used the textbook for a while, but I finally have retyped it with the common ones. If you get to chemistry, there's a larger list of polyatomic ions you'll need to know. In chemistry, you will have to have them memorized, or I'll teach you the pattern for how to come up with their formulas as a shortcut. I do want to point out that polyatomic ions do not always have to be written inside of parentheses, but if I take the sulfate ion, for example, and you can find it there on your page, sulfate is an SO4. And usually we write it inside parentheses, and it has a 2 minus charge. That is, this whole thing has a charge of 2 minus. Anyway, moving on. First, I get rid of my notes here. So, an ionic bond is then when atoms bond together, specifically ions bond together, but it's a bond that forms between a metal and a non-metal ion. If you want to be picky, it can be a polyatomic for either or both of these, though again you only have one positively charged one. Also, as a side note, we usually write the metals first and the non-metals second. That is, we write the positive thing before the negative thing. It forms when one atom gains and one atom loses electrons, which results in it having a charge. And so what's actually going on in an ionic bond is not that usually two ions come across one another, but two atoms come across one another, and the transfer actually happens there as this one loses its electrons to that one there, which is gaining them. And then because of that, they end up with opposite charges, and they didn't necessarily want to end up bonded to one another, but opposite charges, as you know, attract, and it results in a very strong bond. It's strong in part because it's held together by electrostatics or static electricity. It's also strong in part because this usually doesn't happen just between two atoms, but instead a group of atoms and another group of atoms. And so then you end up with this pattern repeating over and over and over again. And this here is probably the most important thing, that the total charge will be neutral when they are bonded. That is, you'll have an equal amount of positive and negative charge. These should have come up one at a time. I'm going to talk through them one at a time, even though they all came up here at once. But the simplest arrangement of atoms is called a unit cell. Down here on the bottom, this is an example of a sodium chloride unit cell. If you want to be really picky, technically unit cells are centered around one atom, and then we look at the things that are bonded around it, and it turns out that sodium chloride happens to have a cubic shape, and so then on each corner of that cube, you would have 1/6 of a sodium sphere. 1/8 of a sodium sphere, and then when you have all 8 of those together, you end up with a whole. If you want to be picky, we're going to simplify it down though and just pretend that is the simplest ratio of the atoms, and you'll get into more details on unit cells maybe in chemistry. Anyway, unit cells end up forming a repeating pattern that is known as a crystal. Up to the top right of the smartboard above the front whiteboard is one of my favorite posters to teach with in the classroom, and right big and centered of that one is also a sodium chloride crystal using the same color scheme, gray for sodiums and bigger greens for the chloride ions there, and that is a sodium chloride crystal. But that repeating pattern is known as a crystal. If you want to be picky, technically oxide and hydroxide ones. That is, oxide and hydroxide ionic compounds are usually not technically known as crystals or as salts. So a group of crystals together we call a compound or a salt, and again, a few exceptions on the salt thing. And the atoms in the unit cell give us the chemical formula, in this case NaCl, which again, hopefully you recall, NaCl, sodium chloride, is also known as table salt. The other thing that we're going to do here, because that's it for notes over ionic bonding, is we're going to get into how you name ionic compounds, as well as how you come up with the formulas for ionic compounds. So we're going to start with the naming process, which is a little simpler. In general, naming, we name the metal first, and then we name the nonmetal second, but we drop the suffix of the nonmetal and we replace it with a suffix, usually "ide," unless it's polyatomic. If it's polyatomic, then if you skim your list, you'll notice it tends to be "ide," "ite," or "ate" as your suffixes. And the only one you need to have memorized is "ide," because you'll be given that list of polyatomic ions and get to refer to it. The other weird thing here is how much do you drop, and to be honest, it takes getting used to it. And so if you look at a periodic table here, I'll go through one time the non-metal side, because the non-metals are the ones that get the suffixes dropped, so that you can hear them at least once. I do not expect you to memorize it. What I expect to see is that you drop some of the name and make an attempt to drop it. So over on the non-metal side, you have carbide, nitride, oxide. I'm going to skip the halogens here for a second. Silicide, phosphide, sulfide, arsenide, selenide, telluride. The halogens all end in "ine," and technically the INE is being dropped and replaced with IDE, but of course that means in all these the N just gets replaced. So we have fluoride, chloride, bromide, iodide, and astenide there on those. So with that in mind, let's name some of these. Now, I start with NaCl here as the example, which was the example on the prior slide, just to start you off with one that you're used to, but Na is sodium, and Cl is chlorine, but being the second thing, the non-metal, the negatively charged thing, we're going to drop the ending and replace it with ide, sodium chloride. 2 words for the one formula there. Next, SrBr2. Sr is strontium. Br is bromine, which we're going to drop the ending and replace as bromide. Something odd happens with transition metals. You may recall that we don't know the charges of transition metals. And part of why we don't know them is because they can take on multiple different charges. So for this, what we end up having to do is figure out what the charge of the iron is here. And we end up having to state that in the name. So transition metals will always have a charge written with them, and we will write that charge as a Roman numeral inside parentheses attached to the metal's name. It'll make more sense when we do it as an example here. So iron, Fe is iron. We're going to need a Roman numeral for its charge. Those parentheses are written butted up right next to the iron without a space there to emphasize that this goes with the iron. We'll come back here in just a moment and figure out what its charge is. Let's go ahead and deal with the oxygen there. The oxygen, the ending gets dropped and replaced with ide. Oxygen, I think, is the one that has the most dropped off of its name. It might be tied with one other. But iron oxide. You may recognize that iron oxide is the common name for rust, is the chemical name for rust. But we need to figure out what the charge of the iron here is. Oxygen, you can look on the periodic table and knowing the patterns that we know, 1 plus 2 plus 3 plus 4 plus or minus 3 minus 2 minus 1, 0, you can know that oxygen has a 2 minus charge. Since there's 3 of them, that must mean that the total negative charge on this thing is 6 minus. If the total negative charge is 6 minus, and we know that the whole compound has to be neutral, that is, it has no charge, then it means the positive charge must be a 6 plus to match. That 6 plus, those 6 charges are split among 2 irons, so we're going to divide that 6 by 2, and we will end up with 3 plus for iron's charge. So that gets written down as iron 3, Roman numeral 3, oxide. Maybe you don't know your Roman numerals. So real quick, just to review them, 1 is I, 2 is II, 3 is III, and 4 is IV, it turns out. And we're not going to deal with charges higher than 4. They do exist within the transition metals, and if you take chemistry, we'll get into those. But 4 is the only oddball one. For all the others, it's writing I multiple times. The last one here coming up with its name, we have these parentheses, which helps tell us that there must be a polyatomic ion here. So the name of that thing, we just get to look up. Now, the other thing I want to point out here is even if there's not parentheses, because they're not always required, I think we get an example here in a moment where it's not technically required, but even though it's not required, I recommend that you write them still. But if they're not there, how do you know? Well, all of these, you'll notice, are made up of 2 elements. They are described as being binary, made up of 2 things. Not binary in that they're made up of only 2 atoms. This one here, of course, is made up of 3. This one down here is made up of 5 atoms, but they're made of 2 different elements, so they are binary. This one here is not binary because it's made up of at least 3 or more pieces. And so when there are 3 or more pieces, there has to be a polyatomic ion in there. Identifying the polyatomic ion then is just comparing it to the list and seeing if you can find one of them that matches. Anyway, getting into naming this thing, Ca is calcium. And PO4, you can just look up on the list and you'll find out that it's the phosphate ion. And so we just call it phosphate. By the way, if we wanted to name the individual pieces of either of these, this would be calcium phosphates made up of 3 calcium ions and 2 phosphate ions. If we're talking about the individual pieces, we always have the word ion there. Once they stick together in ionic bond, that is assumed, and we can drop the word ion for the name. So that is how you name ionic substances. And next, we're going to get into the reverse process where you're given a name and asked to come up with the formula instead. So here we have sodium chloride. For writing the formulas, we got to be able to figure out a way to figure out those subscripts that we had just a moment ago. And so you'll notice that those subscripts did not enter the name, and that this one here, the iron 3 oxide, that the 3 here was referring to its 3 plus charge and not to the subscript on the iron. So how do we know those subscripts are there? Well, it turns out it comes from their charges. So the first step to coming up with the formula, and again, I have a simple one here to start out with, one you've already seen twice here in these notes. Start out by writing the symbols of each piece. So sodium chloride is Na and Cl. And by the way, just so you're not tripped up, the "ide" here, of course, means that this is chlorine. Chlorine is the chlorine atom with 17 protons and 17 electrons. The chloride ion is a chlorine atom that's gained an electron. And so we have the charge. That brings us to the next part of figuring out this formula. We end up having to have the charges here. And so you look up the charges on the periodic table using that pattern that we mentioned just a moment ago, 1 plus 2 plus, skip the transition metals, 3 plus, 4 minus, or plus 3 minus 2 minus 1 minus 0. By the way, because the noble gases are 0, they'll never ionically bond because they're already filled up. But at this point, we need to figure out what the simplest ratio of these two. Now, it should be obvious here because we're only going to need one of each for it to be neutral, so we're going to have NaCl for the formula. Going across, the next one is aluminum oxide. So aluminum is Al, oxide or oxygen is O. Charges on each of these, aluminum is a 3 plus and oxygen is a 2 minus. Here it's going to take a little bit of figuring out. So how many aluminums do we need to cancel out with how many oxygens? Well, it turns out that one of the simplest things you can do is multiply by the charge of the other one. Now technically it's the number of the charge and not the whole charge, so we're going to multiply the aluminum here by a 2, and we're going to multiply the oxygen here by a 3. And keep in mind this is multiply. And so then that means that we would have a 6 plus here and a 6 minus here. Hey, that's going to be neutral. So then we can just use those things that we multiplied by, Al2O3, as our formula. In fact, my students in the past have called this the crisscross rule, because you can just take the sign, or excuse me, the number on the charge, ignoring the sign, crisscross them, and end up with a proper formula. If we came back here to NaCl, there's an invisible one there that we bring down here, an invisible one here that we bring down there, and we end up with the formula. And the question I always get asked at this point is, does that always work? And the answer is almost always. There's just one thing you have to check at the end, which we'll get here in the next one. So we have lead 2 sulfide. So lead is Pb, sulfide is sulfur, so S. Charge, lead. It's in that 4 plus or minus column, but it's the other metals and the transition metals can have various ions, and this one here says that this charge must be a 2 plus. So, okay, Pb2 plus, sulfide 2 minus. And so then when we crisscross these here, we're going to end up with Pb2S2. Well, if you'd paid close attention, like the sodium chloride here, it only took one of each because they had the same charge. Here they have the same charge, so it should only take one of each. Well, it turns out that if you look at this, these are the same subscripts here, and when we have the same subscripts here, we can always reduce or simplify whatever math term you prefer there down to PBS. And so as long as you check and make sure that it doesn't simplify or can't simplify, yes, the crisscrossing always works. It always works. So take the two charges, crisscross them, and then make sure that they don't simplify. By the way, the times where they're going to simplify is when you have the same, that is a 1 and a 1, a 2 and a 2, and so on and so forth, or when you have a pair of even numbers, that is a 2 and a 4. It's the only times it will happen because we're not going to get into charges higher than 4, so it's only when they're both even and not the same that it can simplify, or when they're the same. But always make sure it doesn't simplify, and then the crisscross thing always works. So calcium carbonate. Here's where you have to be careful. Calcium, Ca, carbon 8. You need to pay attention to the suffixes on all these things. This one here is not the "ide" like the others. It's an 8. If it is not an "ide," you need to check your list of polyatomic ions. By the way, if you scan your list of polyatomic ions, I'm pretty sure there's the hydroxide ion there. That one does end in "ide." Be careful with that one. And I don't recall if cyanide is on there as well. It's the only other polyatomic ion that's common that I know of that uses the "ide" suffix. Cyanide, by the way, is the poison that you've possibly heard of before. But since this one has a different ending, we need to look up its formula on the polyatomic ion list, and you'll notice that it is a CO3 with a 2- charge. Now I'm going to write the charge here in a different color, and like I've mentioned already, it's always nice to put this thing inside of parentheses. Before we can do the crisscross thing, we need to look up calcium's charge, which is a 2+. Now that we have it, do the crisscross thing, and just like the prior one, this one here, we're going to end up with two 2's again, Ca2, parentheses, CO3, parentheses 2, and we can simplify or reduce this one. Wait a second. Isn't there an invisible 1 there, and isn't there a 3 there? Those don't reduce. Well, you never change the formula of a polyatomic ion. You never change the formula of a polyatomic ion. I want you to say it with me this time, even though I may not be here to hear you. You never change the formula of a polyatomic ion. But you can reduce the subscripts that are on the outside of the polyatomic ion with a subscript on the thing that's not a polyatomic ion. And so, in this particular case, our final answer is CaCO3. Because there is not a subscript outside the parentheses at this point, technically they are not required, but I always recommend them because it'll make it when we get to chemical reaction easier when we get to chemical reactions in 2 more chapters after this one. So that is how you write formulas from names. And at this point, I have a slide here of practice for you. So I want you to try these 4 on your own first. Pause the video here in just a moment when I'm done with directions. Try these on your own. And then once you have tried them, let's say maybe 5 minutes, a minute to do each of these and a minute to check your work, then I want you to pair up with the person near you and double check your answers and discuss. Take a couple minutes to do that, and then I want your pair to check your answers with another pair. Take maybe a minute to do that, and then you can unpause the video and check your answers against what I have here. So go ahead and pause the video and take a stab at these 4. Welcome back. I hope you have the answers down already and are confident about them. I'm not going to take the time to explain these because hopefully you guys have discussed and figured it out. And if you and your group of eventually 4 got it wrong, find a group that got it right and have them explain it to you. Make sure you understand this. Anyway, the first one here is barium phosphide. The one underneath of that is copper 2 carbonate, and that is Roman numeral 2 inside of parentheses. Our next one here is NH43N, and our last one is ZnSO3. And parentheses not technically required on the sulfite polyatomic ion there, but are absolutely required on the ammonium nitride. By the way, these subscripts are, or this subscript here is distributive, which means there's 3 nitrogens and 12 hydrogens, but do not distribute it out because you can always simplify it down to the simpler version here. Real quick, there is a typo on this one that I just happened to catch. This should be BA 3P2, not that it changes its name. My bad on that. Common mistakes would be forgetting the Roman numeral here on this one, having the wrong suffix on the polyatomic ion there, reading this one as sulfide with an S or sulfate, which was an SO4. Forgetting the charge on the copper, I think I've mentioned already, not having the parentheses around the ammonium, or maybe failing to crisscross properly. Anyway, again, if you got any of these wrong, please do check with one another and make sure that you understand how to do these properly. And after that, you're getting some practice to do as homework, though you should have some class time here to work on it on your own.